Today we're going to continue talking about integration by substitution, and just as important, not integration by substitution. A lot of times we start cutting out some of the details when we're trying to remember what we need to know. For substitution, we need to identify something to be the inside function. Then we need to make sure that we have the derivative of the inside as a factor. That last phrase, the as a factor part, is the part that we forget about. The dw, whatever it's going to be dw, can only be included as a factor. It can't be sitting inside some other function. It has to be its own factor. So g of x is our inside. G prime of x dx is the derivative of the inside as a factor. So we're going to make the substitution. W is equal to g of x. That means dw equals g prime of x dx. We need this dw as a factor, not inside some other function. So we need that dw as a factor, not sitting inside some other function. Yesterday, I put up a couple of examples that I wanted you to look at. One of them was x over x squared plus 1. In this case, we can see that there's an x squared plus 1. The derivative of that is an x, and we have x as a factor. And the x squared plus 1 is sitting inside the 1 over x function. So this one is a substitution problem. The thing that might jump out at us first is we see the x squared and an x. So it makes sense for us to say x squared is our inside function, is going to be our g of x, and x is going to be the g prime of x. And that's exactly what happens here. If w is x squared plus 1, then dw is 2x dx. And that means that 1/2 dw is x dx. So that means I can replace the x dx with a 1/2 dw. I look at my integral and I have x times dx as a factor. We're all set to go. We have to identify the function that we're actually going to be integrating. X dx is going to be replaced with the 1/2 dw. That's just part of our integration machinery. And the x squared plus 1 is sitting in the denominator. So our outside function, our f prime, is 1 over x. Our outside function is 1 over, well, w. So we've identified the three things. We picked something to be the g of x. We found that, pick something to be the dw. We picked something to be w. We have a constant multiple of dw as a factor, and we've identified what w is going to be in, the 1 over x function. So we can make our substitution. I'm going to factor my 1/2 out, as we do. And then our new integral. we're integrating the function 1 over w, and the x and the dx are all getting replaced with a 1/2 dw. So there's our substituted. There's our w. So now we just have to integrate. The integral of 1 over w is the natural log of w. I still have this 1/2 as a factor. The integral of 1 over something is the natural log of the absolute value of that thing. We've integrated so we could put our constant of integration plus c. Three-quarters of the way there now. Let's call it 80%. Let's categorize this w, the dw, and all that stuff. That's 1, 2, setting up your double integral, w integral. 3, integrating your w integral. 4, replacing w with your expression in x. So we end up with a 1/2 natural log of x squared plus 1 plus c. Note that at this point, I simplified my expression. I had natural log of the absolute value of w, but then when I replaced w with x squared plus 1, we noted that x squared plus 1 is always positive because we're only allowed to use real numbers at this point in our mathematical career, at least this point in our calculus career. So I'm going to simplify. I'm going to get rid of the absolute value signs and just put regular old parentheses. X squared plus 1 will always be positive. There's no need for absolute value signs. Note x squared plus 1 is always positive. So we can simplify our grouping symbols. This be regular old parentheses. Yeah. The x is part of the dx. The x and the dx got replaced with 1/2 dw. X dx is equal to 1/2 dw. The x is only there to make this a substitution problem. It was there so it could be the derivative of the inside. It could be my dw. Any questions? Here's one of the things that takes getting used to. For a long time, for most of our algebraic, or for most of our mathematical career, back in algebra, we called variables just one instance of the variable. We solve for the one instance of the variable, solve for x. In this case, we're not really solving for x, we're solving for x dx. That's one thing that we're replacing with 1/2 the dw. It's not that the x is the 1/2 and the dw is the dx. That's not how it works. The x times dx together as one thing is being replaced with 1/2 of a dw as one thing. It takes getting used to. If things look weird, that's the correct answer. This is we've only done substitution for a couple of days. Of course, we have done like 7 problems, so we should be super experts at it by now, right? Incidentally, the answer is no, we could not be experts at this. We've hardly done any problems. There are other ways of making this substitution. There's one more that I can think of, and I don't like it. So we are gonna talk about this, but I'm gonna wait till you all are better at this. What I mean by that, I suppose, is that maybe I'm trying to indoctrinate you into my method, and then I'm gonna talk about this other method, but it might work for you better. But that's going to be secondary to the point that I want to make with our example here today. Remember yesterday, I said compare this x over x squared plus 1 with x squared plus 1 over x. So just flip it over. So this problem is not a substitution problem. We see elements of things that make us think about substitution. I see an x squared, and then I see an x. But I don't, in this integral, have a factor of x. This x is in the denominator. So it's not a factor of x, it's a factor of 1 over x. And 1 over x is not the derivative of x squared plus 1. So we should note that the substitution w equal x squared plus 1 is not appropriate because we don't have anything to be the dw. So the substitution w equals x squared plus 1 won't work here. The reason is we don't have anything to be the dw. We don't have a dw, which is a multiple of x dx, because the x that we have is in the denominator. That's a 1 over x, not an x. The x that we have is in the denominator. So it's a 1 over x, not an x. That's why we're notation. That x is in the denominator. It is not an x to the power of 1. It is an x to the power of negative 1. It's not going to be helpful to make this substitution x squared plus 1. If I had sitting inside my function a natural log, that would be excellent, because then I can make the substitution w equals natural log of x. Then dw would be 1 over x, and I have that to work with, but I don't have any natural logs, and most certainly this x squared plus 1 is not going to work. Fortunately, we can just algebra our way through this problem. I can use the distributive property and make terms that are powers of x. So in this problem, we can use the distributive property instead to rewrite our integral of x squared over x as x squared over x plus 1 over x. Just distribute the over x part. X squared over x we can then simplify. Substitution was not necessary in the beginning anyway. But what this problem is set up for you to do, especially since we're thinking about substitution right now, since substitution is what we spent the day talking about, when I wrote this integral down, we might look at the x squared and the x and think about substitution, because here's w and here's the dw. But this can't be the dw, it's in the denominator. I'm going to put it here. Integral of x is a half x squared. Integral of 1 over x is natural log of absolute x plus c. So this was still one that we could do, but it's not going to use substitution. One of the tricky things in math class is when you learn a new technique, you're primed to try to just use that technique. So if I want to make people lose points, I put integration by substitution right at the top of the quiz, and then I put this problem on there first. Because it's like, well, it says substitution right there. So then you try to force this into a substitution problem. That's kind of mean on my part. But knowing how to do substitution is knowing when not to do substitution. It's like if you teach kids a martial arts. You teach the kid how to throw a proper punch. But along with that, you teach the kid, you don't want to do this. You don't want things to come to that. You teach them when not to throw a punch. Not just how to throw a punch, but not when not to. Same kind of thing. I could prime you with substitution by calling this quiz, integration by substitution. Or if I wanted to make it more threatening, test, integration by substitution. And then put this problem first. And then you'd be like, oh, well, this doesn't seem like a substitution. Your instinct might be to the point where you look at this and say, that's not substitution. But then your stupid logical brain will be like, oh, but it says substitution on the top. So I'm going to try to do substitution on this. And then you're like, oh, okay. And then you make that mistake, then you get the quiz back, and you're like, oh man, I'm the only person that did that. I feel so bad. I'm so bad at math. But you have to realize 30% of the people in the room did that. So don't think that you're special because you got a problem wrong. Because students think that way all the time. 40 people in the room, and you're not going to ask a question because, like, oh man, the 39 other people understand what's going on. So I'm not going to ask a question. As if by asking a question, I'm going to identify you as the weak member of the herd and have a lion drop out of the ceiling and eat you. Well, dude, that's not how this works. If you're like, oh, I don't know what's going on, there's probably at least 2/3 of the class that are like, oh, agree, do not know what's going on. But no one says anything because they feel like they're the only one. I'm very sorry to report, you're not special. Most people don't know what I'm talking about. I have years of experience, decades of experience of people not understanding what the heck I'm talking about. To the point where in conversation, I just assume that no one knows what I'm talking about. Yeah, still ask, you know what I mean? Very often. So I also threw in the one that we already knew. Integral of 1 over x squared plus 1. There's no substitution here. It's just an arctangent. So this one I threw in there. It's just an arctangent. One that I didn't throw in. Actually, I'm just going to give you one to think about. No reason to do these, not give you an opportunity to check all this cool stuff out. Here's our next one to think about. I'm not going to do these. I want to give you all an opportunity to think about these problems. Here's what I will say, even though the title of this discussion is substitution versus not substitution, both of these integrals are substitution problems. So those are that's your next pair of integrals to think about for tomorrow. Both of those integrals are substitution problems. One of them is just more obvious than the other one. One of them is super obvious. One of them is calling back the one right above it. So think about that. Speculate about how the substitution is going to go, and then try it. Not right now. Save it for later. If right now you don't see it, you've seen the setup of the problem. Later on, you might look at it and say, oh, clearly it's this, because your subconscious is going to be working on the problem. That's why I want this problem in your subconscious. Both are substitution problems, though. So the other comparison that I had was the integral of, I think it was x plus 1 over x. Did I use plus? I think I just dropped the plus, or the square. So this problem is interesting because it's in the substitution day. It's on substitution day, but there's no obvious substitution here. And since we did that x squared plus 1 over x, you might be thinking, shouldn't we just use the distributive property? And we absolutely should. If we can write terms that are powers of x, then we should write terms that are powers of x. I'm going to write this as x over x plus 1 over x with the distributive property. No substitution required here. And then I'm going to rewrite the x over x as 1 . So no substitution required here. Just use a distributive property. So the integral of 1 is x. The integral of 1 over x is natural log absolute value of x. And then we plus c for our constant of integration. The other problem to compare with this one is the reciprocal. So there's no obvious substitution here. There's no x squared, derivative is x, or x cubed, derivative is x squared, or x to the fourth plus 1, derivative is x cubed. There's no obvious substitution, but it's also not a distributive property. That's not how the distributive property works. 2 plus 3 over 5 is 2 over 5 plus 3 over 5. But 5 over 2 plus 3 is definitely not 5 over 2 plus 5 over 3. Don't be all making up algebra rules. Algebra rules weren't made up. That's just how numbers work. Algebra should be framed less about its own thing and more about an extension of arithmetic. At the beginning of an algebra class, it's like, oh, hey, remember numbers? Yeah, instead of base 10, we're going to be using base x. And if we properly taught you arithmetic, you'd be like, oh, gotcha. But we've decided to make life difficult for everybody on the planet and only teach how to count base 10. So there's no obvious substitution, but it's also not the distributive property. No obvious substitution. So this one is a little bit sneaky. Here's what we're going to do. This x plus 1, we can imagine as sitting inside the 1 over w. The trick here is recognizing that if I make w equal to x plus 1, then dw is equal to dx. The only thing that's going to be left over, I'm going to make the x plus 1 w, dx is going to be replaced with dw. I don't need the x to make the dw. Dx on its own is the dw, but I still have this x left over. But take a look at the substitution that we're going to make. I'm going to say w is equal to x plus 1. There's an ant on my pen and I was going to blow it off. And then I remembered. Pretty good. I had a little bit of coffee this morning, so that occurred to me before I was sitting there going and spent the rest of the time. Oh, what the heck? If I make the substitution x plus 1, we have to think about what is required to make that substitution go. That means that dw is equal to dx. But this leaves us with a problem. What are we going to do with that other x? So the x plus 1 can get replaced with w. the dx can be replaced with dw, but that doesn't take care of everything. Notice that there's still an x. And it's gonna be offensive to your eyes to see this dw with an x still sitting in it. So watch out. Is everybody mentally prepared for this? Am I mentally prepared for writing this? Oh, now the answer is on me. Oh my God, ugh, I can barely look at it. That's a dw integral, and that stupid x is still sitting there. Ugh. We got to do something about this other x. Fortunately for our heroes, we've made such a simple substitution. W is equal to x plus 1, and I can turn this around and solve for x. I gotta do this quickly because this is really offensive. I can turn my substitution around to replace the other x. So my integral w is still in the denominator, but my numerator can be written as w minus 1 dw. Whew. That was close. Kind of reaching my limit with that friggin' mixed integral dw and the x all at the same time. Questions? Now it is a distributive property problem, so we like it. Now everything is cool. I can write this as the integral of w over w minus 1 over w. dw. And then I can simplify the w over w to be 1. This is not the answer. This is still in the language w. I translate it back to the language of x. So w is equal to x plus 1. And I'm still going to need my absolute values around the x plus 1 because it might be negative. Any questions? Any questions so far? A little bit sneaky on our part because there wasn't an obvious w and dw at the outset of the problem. But we encountered a different kind of problem because there was no distributive property available for this. Those are really only two things that we know how to do right now. Like tomorrow, you'd be able to use parts on this, but we're not there yet. It's not tomorrow. And some of you are like, oh, no, I don't experience time like the rest of you humans. I have done parts because this is all happening at the same time. So we did have to use our substitution technique in a little bit different way. Because it got us to a point where we could use a distributive property. Two terms in the denominator is inconvenient. One term over two terms, inconvenient. Two terms over one term, distributive property. So we used our substitution to get us there. Now, the other thing that's disturbing right now is I have to put a box around this as an answer. And here's why. you go and look this up on Wolfram Alpha, there's going to be something missing. It's just going to say this. Actually, I'm just pretty sure it's going to say this. And this is going to raise an important question. What is the important question that this is going to raise? What happened to the +1? That's exactly what happened. That's exactly the question that we need to concern ourselves with. At this point, you're like, oh, yo, Leach, you forgot the +1. Here's why we don't need the +1 in our answer. C is an arbitrary constant. If C is the constant 4, if this C is the constant 4, then this C is just the constant 5. It's an arbitrary constant. Adding 1 to an arbitrary constant gives us another arbitrary constant. As long as all we're doing is constant stuff to the arbitrary constant, we just replace it with another constant. So we don't need the +1 because C is an arbitrary constant. So we don't need the +1. Another way to think about it is that C +1 is just some other arbitrary constant. So we just write +C. We only get to determine the +C if we have additional information about the vertical placement of a particular antiderivative. If I told you that f of, can we use 0? Yeah. If f of 0 is equal to 5, down here, someone would just say, oh, C is equal to 5. Up here, someone would say C is equal to 4. They'd add it to the 1, and you both come up with the same function. Here's the tricky part. If you put that +1 in there, I take off 1,000,000 points and you go all the way back to algebra class. I'm just kidding. I totally don't care. We should simplify our constants, but at this point, this is kind of a new one, and I'm not really concerned about it. It's not wrong to leave the +1 in there. So either of these answers are okay. If you're typing things out, you don't need to check to see that your arbitrary constants are arbitrary. And so if you're not sure, just leave the +1 there. Okay? You're all saying, yeah, this is okay. This is super not okay, because I'm giving you multiple choices for what the answer is. I say both of these are acceptable. So it's important to understand why both of those are acceptable. Does that make sense? I try to create clear communication here. And I just said, yeah, either one. And that's a little crack in our clear communication. But we're new, so it's okay. It's like when little kids are learning to communicate with the words that they observe the adults around them and the other children around. You cut them some slack if they say me instead of I, or if they say I instead of me. You know what I mean? And we think it's adorable. Other instance of this we have is whenever we have two terms where it's inconvenient, but we've got a spare x running around, and we can get those two terms out of the inconvenient location. So for example, if we had the integral of x times the square root of x plus 1, this would be an opportunity to use that same substitution. Some of you would try to move the x inside and have the square root of x squared plus x. Oh, sorry, an x out here is an x squared. X cubed plus x squared. But then you would try to distribute the radical. But the radical is exponents, and exponents do not distribute over addition. This is a good opportunity to see where your algebraic understanding lies. Is it based on form, or is it based on reading and understanding what the symbols are telling you? Well, we know that the square root of 4 plus 9 is not 2 plus 3. I can't just distribute the radical over the term. But from an integration standpoint, 2 terms is inconvenient inside of a radical. I would rather that just said w to the 1/2 power. And I can get there by making the same substitution that we did before. W is equal to x plus 1. That means dw is equal to dx. That takes care of this x plus 1 inside the radical. That takes care of the dx, but this x is still hanging out. And that's okay. We can turn the x plus 1 equals w into x equals w minus 1. I don't know why I felt like I had to cram this problem way up in here. So the x is going to be a w minus 1. The square root of x plus 1 becomes the square root of w, and the dx is dw. This is more convenient because now I can just distribute a w to the 1/2 power. We should come up with this name. We should come up with a name for this technique where we take 2 inconvenient terms and move them somewhere. We get the square root of 2 terms, annoying, square root of a single term. I can write it as a power of w. Any questions? Another important thing to note, I'm the only person that gets to stop a problem with ... You can't be like all writing some test and like, oh, then there's some other stuff, and then put ... at the end of it. ... in the context of a math problem says, y'all do the rest. And if on a test, you say, you know what, Lee, you do the rest of this problem. I always get it wrong. For some reason, when I'm grading tests, I can't do anything anymore. I'm like, oh, well, let's see, I'll do the rest. I got 5. That's not the answer. So minus 1 billion points. I'm just kidding. It's only minus 4 points for the problem. But it is minus 1,000 points for the hubris of making me do the problem. I'm the instructor. All hubris belong to me. I'm just kidding. Any questions? So finish this problem out, see how it works, see why it worked that way, and also think about these 2 substitutions. What are the substitutions in each of these 2 functions? All right, that's going to do it for today. We'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.